So let's talk about the shape of our histogram plot, right? And so remember, a histogram is just a visualization of a frequency distribution. Along the x-axis, we have all the various values, either binned for a continuous variable, or we have the values themselves for something that's more discrete. All right, and then we have frequencies here on the y-axis. So again, we use our, well, it doesn't really matter, right? So whatever our values are, because I just want to talk about the shape. So we talked about, right, we have measures of central tendency, such as the mean, that tell me the middle point, right? And we can also use the median to give a middle point, or also the mode, which is the most values, is also kind of a measure of central tendency. It is a measure of central tendency, but it's kind of an idea of where the middle is. And we talk about the spread around, right? The variability, which we know is variance or maybe range, gives us an idea of the spread around that middle piece, right? So with our measure of central tendency, the mean, the median, or the mode, and we have some measure of variability, such as the variance, the standard deviation, which is just the square root of the variance, or the range. We also look at the shape, right? And I talked about this before. We can talk about the skewness, right, which is a measure of the symmetry. So in this example, we have what looks to be a very symmetric distribution, right? It might not always be the case that it's so symmetric, right? And so we might have a case where we have a very positive skew, right? Or we might have a case where we have a negative skew, right? So they can be skewed, which again is a measure of that symmetry. And also we talk about the kurtosis. We can have something that's very platykurtic, such as the uniform distribution, very flat. We can have something with a lot of peak, right, which is leptokurtic, or we can have a shape that is kind of mesokurtic. And obviously we can have various examples, right? So this would be mesokurtic but skewed, right, as opposed to leptokurtic with a positive skew, right? So these combine among each other. Now, we like, in statistics, we like this kind of bell curve. In fact, we like it a lot. And we call this bell curve the normal distribution. Sometimes it's also called the Gaussian distribution, named after the scientist who first discovered it in biology. The Gaussian distribution, the normal distribution, has certain properties which are very valuable to us. One thing that's important about the normal distribution is it's called the normal distribution, at least in part because it happens very naturally. The normal distribution is a very natural distribution. We find this all over the place. We find it in nature, we find it in human psychology. For instance, personality scores in general, people's personalities tend to fall, certain traits fall along a normal distribution. So most people are somewhere in the middle, and then as we get further away from the midpoint, we get more extreme values. The normal distribution also provides us with some really useful properties for use in statistics. So first let's talk about the properties of the normal distribution itself. The normal distribution is one that has a couple of important properties. First of all, the mean is equal to the median is equal to the mode. So all three measures of central tendency will be identical in the normal distribution. The mean is equal to the median is equal to the mode. It is also perfectly symmetric, right? So there is zero skew. It has a skew of 0, and it is perfectly symmetric. It is also perfectly mesokurtic. It's not too high of a peak, and it's not too flat, right? It's kind of that Goldilocks curve. It's perfectly mesokurtic, right? So again, it is kind of that Goldilocks curve. It's right in the middle. It's nice and symmetric without being too high or too low. It's just kind of that nice curve. Now, we can put numbers to this, right? And so when we ask a computer program for certain descriptive statistics, it'll give us the mean, the median, the mode. And they might not be exactly the same. They might be off by a little bit. And so our question starts to become, okay, how far from the normal distribution can we stray while still using the normal distribution? And it's fairly robust, but we at least want to be aware of it and make sure we're looking at our data to make sure that they actually are distributed normally. So I said that the skew we want to be 0, which means perfectly symmetric. And really, anything that ranges from -1 to 1 and our skew, right? We actually get a skew score. Anything that ranges from -1 to 1 is generally considered to be close enough to 0 as doesn't count, right? And we can get a little bit over that, and you can look at it, and there's various other decision-making methods that you can use, but for practical purposes, -1 to 1, right? And the same thing for kurtosis, right? You want a kurtosis also of 0. -1, right, would suggest very flat. +1 would suggest very leptokurtic. And so generally, again, -1 to 1. That's not absolute, but it's a good guideline to go by. Now, I'm not going to get into it because it's kind of beyond the scope of this course. If you take more advanced statistics course, we could talk about it, but you can actually transform if the shape doesn't work out right. So something that is very skewed can actually be transformed arithmetically into a more normal distribution. It's certainly, there's some disadvantages to that. It has some impact on how we interpret the results, but it allows us to use our normal distribution. Interestingly, we can add and subtract from a constant to all the numbers in our data, and it doesn't actually change the shape of the distribution. But when we do some other stuff like multiply, divide, take square root, square, take a logarithm of it, etc., that can actually change the shape. Just adding and subtracting a constant doesn't, but doing other things to it can change the shape. And so we can actually, if we don't have a normal distribution, we can transform into the normal distribution through some of those methods. Again, kind of beyond the scope of the course for right now, but just be aware it's a possibility. Now, why are we so vested in the normal distribution? Well, again, partly because it's so common, but also because it has this really cool property around probability. And it turns out that within our normal distribution, right, most scores, right, the mean is equal to the mode. So most scores, or I shouldn't say most scores, I say the highest number for, or highest frequency for any particular score is also the mean, right, which would suggest that really, like, most people are, and everyone is, not everyone, most people are somewhere close to the mean. That's a valuable thing. Not only that, but we can actually define that down. 68% of our sample is within plus or minus 1 standard deviation from the mean. Right? So if I go out 1 standard deviation above, remember the standard deviation is the square root of the variance. If I go 1 standard deviation above and 1 standard deviation below, then I know that 68% of my sample is inside of that. 68% of people, their scores, or 68% of instances, their scores are somewhere in this range. I can go out further to 2 standard deviations of the range, two standard deviations, and it's not quite 95%. It's actually not quite 2. It's actually 1.96 and negative 1.96. Then 95% are within approximately 2 standard deviations. Right, so now this is a 4 standard deviation spread, 2 below, 2 above, but within that 4 standard deviation spread, 2 above the mean or 2 below the mean, 95% of our sample is inside of that. 99% is within 3 standard deviations of the mean. So that becomes very useful from a probability perspective. If someone is 5, 6, 7 standard deviations away from the mean of our sample, then we start to question whether they are part of a different population, right? Or if I have 2 samples that I look at their means and they're not within a couple standard deviations of each other, I might start to say, well, each of those samples comes from a different population. That's the root of our understanding of statistics and the way we use statistics in IO psychology, is this idea that most of our values for any particularly normally distributed variable should be close to the mean. 68% within 1 standard deviation of the mean, approximately 95% within 2 standard deviations of the mean, approximately 99% within 3 standard deviations of the mean. That's why the normal distribution is so important to us, because now we can make some judgments and some inferences about the location of a particular data point or the mean of a different data set as compared to the mean of the normal distribution given within intervals of certain standard deviations. So normal distribution, very important. And And look, it doesn't have to be perfect. I want to add this at the end. It doesn't have to be perfect, right? I already gave you kind of some parameters around skewness and kurtosis. And sometimes we'll look at shapes and say, oh, no, that's really normal. It's really close. It doesn't have to be perfect. Most of our methods are actually fairly robust against not having a perfectly normally distributed. But it also can't be a mess, right? We can't have a ton of outliers, or it can't be really horribly skewed or really horribly leptokurtic to the point of essentially being constant, or very platykurtic, right? Because that will actually really disrupt our this piece about 68% being here and 95% being here. It really disrupts those probability distributions, so we have to be careful of that. There are some ways around it. Larger sample sizes helps. It makes us, chances are we're closer to a normal distribution when we use a larger sample size. We can do some transformations, as I alluded to earlier. There are some tests that don't require a normal distribution. We'll talk about, later in the semester, we'll talk about non-parametric tests that don't require a normal distribution. So there are things that we can do, and also multiple samples. Anyway, there's other things that we can do. But a lot of our stats of our most robust tests rely on a normal distribution, and we want something that at least approximates. It doesn't have to be perfect, but we do want to at least approximate it.